All right, we got William joining the chat. And now we are live on YouTube. Perfect. Okay, YouTube live is good. Okay. So for everyone joining right now, we are going to start the presentation in about 5 minutes. We're just going to let people trickle in. If you have any questions for Avani after her presentation, feel free to put a hand up here in the Zoom call. If you're on YouTube live stream, feel free to put anything into the comments. I'll be monitoring the live stream, so I'll make sure to read out any of your comments. But yeah, we're just going to let people trickle in for the next 3 or 4 minutes. So just updating people who have joined the YouTube live stream. For everyone in YouTube live stream, we're going to start in about 3 or so minutes. Just let some more people join. If you have any comments at all during Avni's presentation, feel free to share them in the chat, and I'll make sure to read them out during the question time. All right. I'll start for this next minute with a quick introduction, and then we can get into Avni's presentation. But hello, everyone, and welcome. Oh, John just had a chat at 4. John, okay, so John just has to leave in a bit. Sounds good. We're starting it off now. Hello, everyone, and welcome to the HQP seminar of January, hosted by the McDonald Institute. My name is Ryan, and I'll be hosting this talk with you guys today. Today's presentation is brought to you by Avani Bhardwaj. Avani is going to be presenting on measuring the refractive index and thickness of aerogel radiators with SD-OCT for the high energy light isotope experiment, also known as HELIX. But without further ado, I will give it over to Avni. Once again, if you're joining us through YouTube live stream, if you have any questions for Avni, feel free to put them in the chat at any time. I'll be monitoring it, and I'll make sure at the end during question time to get your questions asked. Yeah. Without further ado, Avni, take it away.
Thanks, Ryan. Hi, everyone. I guess my goal of the talk today is to make sure that you all understand the title of my talk, which I realize is a bunch of words that don't make much sense. So without further ado, oh, sorry, I keep forgetting. The outline of my talk is I'm going to start off by talking about what cosmic rays are. What can we learn from cosmic rays? What are aerogel tiles, or what's aerogel? What's spectral domain optical coherence tomography? And then how can we get refractive index and thickness using SD-OCT? So what are cosmic rays? Cosmic rays are high energy particles that travel near the speed of light. They're made up of 90% hydrogen, 9% helium, and 1% of heavier elements. They can tell us about space and universe, so they travel very large distances across the universe before they arrive onto the Earth or the atmosphere. And then we know that their kinetic energy ranges from 1 MeV up to 1 exaeV. And then I read this quote online that it gives an analogy. It's the range is from less than the energy of a flying mosquito all the way to the energy of a tennis ball whacked at 100 kilometers per hour. So that's what we know about cosmic rays. Here's what we don't know. We still aren't sure where they come from. There are lots of theories. There are lots of theorists working on simulations and trying to understand. They could come from supermassive black holes or from starburst galaxies. We don't know how they get accelerated. There's a lot of also theories of trying to understand how do they reach at such high speeds that are close to the speed of light. And then a question that the experiment I was working on, HELIX, that's trying to answer is how long have they traveled in our galaxy before they arrive to the Earth or the detector that we're trying to measure. So how can we measure cosmic rays? There are three main methods to measure cosmic rays. We've got ground-based observation, satellites and spacecraft, and balloons. The image here in the background is of the ISS looking down on Earth. This is an astronaut doing a spacewalk on an experiment that is actually on the ISS studying cosmic rays. It's called AMS. Here I believe they were fixing some part of the detector. It's pretty cool. I think there's a documentary on Nat Geo about the spacewalk. So what are ground-based observations? Essentially what happens is when a cosmic ray enters the atmosphere, it interacts with the atmosphere and then creates a particle shower. From that particle shower, we can have arrays of detectors that can measure this particle shower and reconstruct the cosmic ray. From this, we can learn what kind of cosmic ray we had, what the energy of the cosmic ray was, and the particles from the particle shower. Satellites and spacecraft, as I said previously, we can go, instead of having the cosmic ray interact with the atmosphere, we can go up into space or above the atmosphere to be able to characterize the cosmic ray. AMS is an experiment that's on board the ISS. It's been on for 14 years, and it's been studying the properties of cosmic rays. And then I guess my favorite, or heavily biased, is balloons. And similar to what AMS does, balloons go up above the atmosphere, about 30 to 40 kilometers high, and they have a flight duration between a couple weeks to a month, where you can observe cosmic rays and measure, again, properties of cosmic rays. Like a fun fact, cosmic rays were just discovered on a hot air balloon by Victor Hess back in like the 1800s. So this technology is still very relevant for us to learn more about cosmic rays. So what are properties of cosmic rays that we're able to measure? I've mentioned this repeatedly. We can measure the energy. So here I've got a plot of the flux, which is the number of cosmic rays or energy per area per time as a function of the energy of the cosmic ray. Up here is what we call the solar cosmic rays that are measured. Over here is where we measure cosmic rays above the atmosphere. So you have satellites and balloon-borne experiments. And then down here is where we have observations from ground-based telescopes and ground-based observations. Another thing that we can measure is the composition of cosmic rays. I should say that cosmic rays have 1% of heavier elements, but I didn't mention what are those 1% of heavier elements. This is a plot of the cosmic ray composition compared to the solar system. So the lines in red describe the elements in the solar system compared to the cosmic ray. Here, a key feature or something that's really important to note is that the solar system has 10 to the power 6 times less beryllium compared to the cosmic ray. And this can tell us information. Another interesting thing about beryllium is that beryllium has one unstable isotope, beryllium-10, that has a half-life of 1.4 million years. So just like carbon dating, where our archaeologists try to get the age of things that they find by looking at the ratio of carbon-12 to carbon-14, we can do the same for cosmic rays. We can measure the ratio of beryllium-10, the unstable isotope, against beryllium-9, which is the stable isotope. And that can tell us how long the cosmic ray has been in our galaxy. Why are we interested in measuring beryllium is what this plot is trying to show. The y-axis here shows the ratio of beryllium compared to the energy. As you can see, we don't have enough data to tell us how long have cosmic rays at what energies been propagating in our galaxy. Another key feature is that the uncertainties of these data points are really large. One way to reduce these uncertainties is being able to resolve the masses of beryllium-10 and beryllium-9 really well. So, how do we measure beryllium? This is HELIX. It's a high-energy light isotope experiment. It is a balloon-borne experiment, and it plans to resolve the ratio of beryllium-9, beryllium-10 for energies between 0.1 GeV up to 10 GeV per nuclei. So HELIX has three main subdetector components. We have something called the time of flight that can measure the charge and the velocity of the particles. We've got the drift chamber tracker that's inside a 1 Tesla magnet. So what this tracker does is it measures the bend of the particle. As the charged particle comes in, if it's a low energy particle, it will bend more than a high energy particle, and that can give us information. And then finally, we have the RICH, the ring emitting Cherenkov detector. This measures the particle for velocities above 1 GeV per nuclei. Because the time of flight, given its the way it measures is simple, it's distance equals velocity times time. So it's limited by the distance of the two paddles, and at some point, the energy of the particle would be so high that you wouldn't be able to tell when it entered and when it left the bottom time of flight, which is why we have the RICH detector. Lastly, what's not labeled in this photo, we have a hodoscope that's placed right above the RICH detector. This is to measure the position of the particle right before it enters the RICH, so it can help us have accurate particle reconstruction when we do analysis. So I've described what we're measuring with the three subdetectors: the charge, the rigidity, and the velocity. When you combine them all together into this equation, you're able to get the mass. And from the mass, you're able to identify which particle is in your cosmic ray. So what are the science goals of HELIX? We want to measure the isotopes of cosmic rays, and we want to measure the ratio of beryllium-9 to beryllium-10 for energies from 0.1 GeV per nuclei up to 10 GeV per nuclei. And this ratio, again, just to remind people, tells us how long cosmic rays have been in our galaxy. So we need to be able to resolve this ratio such that we can distinguish the two peaks. Beryllium-9 and beryllium-10, their atomic mass unit are very close, and we need to be able to have a really good detector resolution or characterization such that we can separate the two peaks very well. Here is a plot of the resolution of the detectors for velocity. The time of flight is in red, and the RICH is over here. We want to make sure that the velocity resolution is less than 0.1%. In order to do that, I'm going to focus on showing you how the RICH is able to achieve such a velocity resolution such that we're able to distinguish these two peaks in our data. So, ring emitting Cherenkov detectors Before I can talk about it, I want to talk about Cherenkov radiation. Cherenkov radiation is this electromagnetic radiation that occurs when a charged particle travels through a medium, and in that medium, it travels faster than the speed of light. When that happens, a blue light is emitted in the shape of a cone. And from that blue light, you can reconstruct with trigonometry the angle at which the emission happened, and you can get information about the particle velocity. So here's an image depicting that. A particle comes in, it creates this wavefront of blue light. This theta c is the angle of your interest. And here's the relationship that describes how you can get velocity if you know the refractive index and you're able to reconstruct the angle. So this is HELIX's rich detector. We have aerogel tiles. This is our radiator. This is the medium that will cause the emission of blue light for a charged particle that passes through. And then over here at the bottom, we've got our SIPM arrays in a checkerboard pattern that will detect the light. And then from trigonometry, if you know the distance between your SIPM array and your aerogel tiles, and you can calculate the radius from the ring or the cone of light that you get, you can figure out what cos theta is. And from that, you're able to get the velocity of the particle that you're interested in. I should mention that the corners of the radiator tray have 4 tiles of sodium fluoride. This is another material with a higher refractive index. This is so that we can do cross-calibration with the time of flight velocities, so that we can ensure that we are measuring the correct value. Now, what is aerogel, or what are aerogel radiators? Here on the right, I have a list of common materials known and the refractive indices of these materials. For HELIX, we want to be able to measure particles above 1 GeV per nuclei. And if you rearrange the equation cos theta equals 1 over n beta and set like a threshold, your n is equal to 1 over beta. And for us, that means we need a refractive index of 1.15. As you can see, it's pretty hard to find a refractive index between air and water. You pretty much have to create it or build it. So this is an image of an aerogel radiator that was prepared for our experiment by our collaborators in Japan. Aerogel is a material with a tunable refractive index. Essentially, it's made up of silicon dioxide and air. It's made in such fashion, you kind of like dry it out, and then you get these nice squares. We made about 34 aerogel tiles, and yeah, they flew on to the flight. We were a bit worried that they would crack and crash, but nothing happened, which was pretty cool. So now going back to this equation, cos theta equals 1 over n beta. The only thing that I can characterize or constrain or control very well is my refractive index here in the equation. And in order for, like, how well do I need to know this refractive index? It has to be good enough that I can distinguish these two masses. Thus, like, a goal for my project was to be able to know the thickness and refractive index on the order of 10 minus 3 and 10 minus 4. The thickness, or what I would say like the surface map, is really important because essentially when we do analysis or we try to reconstruct the particle path, it's not as simple as cos theta equals 1 over n beta. We would care about at what point on the top surface of the particle did the top surface of the aerogel did the particle enter. We'd care about how it exited, where did it refract from. So this is why we also want thickness in order to reconstruct the Cherenkov cone. So now I'm going to introduce spectral domain optical coherence tomography. This is a method that I use to be able to measure the refractive index and thickness of aerogel radiators. Just to give you some background, optical coherence tomography was a method invented in the 90s, and it was mainly used for the purposes of biomedical imaging. If you ever visit your ophthalmologist, occasionally they will use OCT to look at the back of your eyes, so your retina, and to make sure it's healthy and well. It's actually very common and used everywhere. Here at Queen's, spectral domain optical coherence tomography is used to is used to image welding. So it's in situ welding. It's pretty cool. Essentially, what OCT does is it's a simple Michelson interferometer. We've got a reference arm and a sample arm. Our reference arm has a static mirror that's imaged, and our sample arm has the aerogel tile in place. We measure the interference between the surfaces of the aerogel tile, so like let's say the top surface and the mirror. It recombines into the beam splitter, and it goes into a diffraction grating where we produce an interference pattern that's based on the wave number of light. So essentially, we have this diffraction grating that kind of bends light by wavelength, and it's read out in a camera. Here's an image of what the setup looks like in the lab. This is what the sample arm looks like. I have my aerogel tile placed here. I have my light source that's placed on a Z stage. And then I have a mirror that's placed below the tile, which I'll explain later why I have the mirror. Essentially what happens is the aerogel tile will move on an XY stage, and the Z stage will image the top surface, the bottom surface, and all the other surfaces in order to get the refractive index and thickness. So a little bit of theory, or a little bit of what's really going on. The camera is essentially imaging, or this is the equation that describes what the camera reads out. And this is what the interference pattern looks like. And if I take the Fourier transform of this, I can get the depth, shown over here in this plot, scaled by the group refractive index. So what that looks like is I'll be moving the light source here. My depth is essentially at which location can I see the top surface, at which location will I see the bottom surface, and so on. So optical path length is equal to group index times thickness. And these are the two variables that I want to know for my aerogel tile. So I've got two variables. In order to solve these two variables, I need to create two equations. So in order to create those two equations, I image the top surface and the bottom surface. I image the surface, the sample, through a mirror, and then I image the mirror as it is. And from these four measurements, I can create a system equations to solve the thickness and refractive index. I should mention that the refractive index I'm measuring is the group refractive index, not the phase index, which we are interested in order to reconstruct the velocity for the rich detector. So how do I get the phase index from the group refractive index? I know that aerogel is made up of silicon dioxide and air, as I had said previously. And there are these equations in the literature that describe silicon dioxide and air as a function of that describe the refractive indices of silicon dioxide and air as a function of wavelength. They're called the Sellmeier equations. These Sellmeier equations, you can fit for these Sellmeier equations to get the group refractive index that I have over here shown. And essentially what I do is I have my OCT data point that I collect, and I try to fit to a combination of air and silicon dioxide. And then I just scale my phase refractive index to that fit such that I can get the phase refractive index at a given wavelength. Here, this blue line is the group refractive index values, and the black dot is OCT. Electron beam data is some data that was previously collected for an aerogel tile, and as you can see, it almost very closely agrees with the phase index fit that I have here. Now that I have this method and I know that I have a way to measure the group refractive index of aerogel tiles and thickness, how do I ensure or try to validate that this method that I am using is true and is correct? I mentioned previously that I have 4 sodium fluoride tiles that were used for cross-calibration. Sodium fluoride is it's a good material. Good in the sense it's got a good crystal structure. That means it's got excellent reporting and literature value of what the refractive index is. So what I did was I measured the group refractive index of sodium fluoride, and I compare it with the literature value. And when I say the literature value, it's like pretty good. This research of the refractive index was in the 70s. Like nobody has reported any improvements or anything. That's how much they kind of trust it. And then when I do my comparison of my measurement, I essentially just take the residuals. So here's a 1D histogram of the residuals of the group refractive index compared to the literature value. There does show a bit of an offset, and what I will note is that the tiles that I was given did not come exactly with a data sheet or some kind of verification of what their group refractive index is. But given that it's like 4 times 10 minus 3 or 4, it's still very in good agreement with the literature value. And to show that I don't really have any systematics or an offset going on, here is the same 1D histogram plotted as a function of position on the tile. Finally, now that I can verify that I've got excellent group refractive index measurements, I can measure my aerogel tiles. Here is a plot of thickness, and here's a plot of group refractive index. On the thickness plot, you can see that the top center of the tile is much higher in value, about 30 microns, compared to the corners. Whereas for the group refractive index, we've got a change or a lower refractive index on this corner, upper left corner, compared to the rest of the tile. And this just kind of shows how important it is for us to be characterizing the thickness and refractive index later on to be able to reconstruct the velocity from the rich detector. And so just to summarize, cosmic rays are pretty cool. We still have lots to learn about them, in particular, how long have they been in our galaxy by measuring the beryllium-9, beryllium-10 ratio. We want to measure all 32 flight tiles. Something I hope to do in the future is to improve data collection. Right now it takes about 10 hours to just measure a single tile. Another thing I'd like to do is, I had mentioned that aerogel is made out of silicon dioxide and air. However, the tiles that were made for us are hydrophobic. That means they do not absorb any water, which is actually pretty great given that they undergo such harsh climate conditions. But that fit that I showed you needs more improvement. I need to implement carbon instead of just silicon dioxide and air. And the photos below, this is the HELIX collaboration on the right, and this is the ultrafast laser lab that I work at. Lastly, I didn't mention this, but now I'm realizing I should. HELIX actually flew. It went up, they're 40 kilometers up into the atmosphere on May 2024, yeah, I think 2024. It was in flight for about 6 days. This is a photo of a GoPro that was on HELIX, which I think is pretty cool, looking down on Earth on a nice sunny day, I hope, somewhere. And yeah, that's all. Thanks.
All right. Thank you, Avani, for the presentation. We are now currently in question time. So if anyone has any questions, feel free, if you're in the Zoom call, to put your hand up. If you're in the YouTube live stream, feel free to put in the chat. I'll be monitoring the chat, making sure that if anyone does have any questions, that they will get answered. Oh, Zoe's got a question. Zoe, go ahead. The mic is yours.
Hey, Avani. Thank you so much for that very awesome presentation. I wanted to ask you about one of your last slides where you've got the results of the aerogel measurements. There's a couple of white
Oh my
dots. Are those like dead pixels, or is it they were outliers so you couldn't use that data? What's up with those guys?
Yeah, I should have mentioned this earlier. Um, I have like this whole bunch of analysis that I do once I collect this data, and these pixels in the corner was just bad data. So they didn't meet like the criteria in order to pass. There wasn't enough signal or light being reflected back from one of the four surfaces that I measured. So yeah, it was just bad data.
Any more questions in the Zoom chat? Feel free to put your hand up now. While we wait, I also have a question myself. If you go back to the Fourier transform slide, I was curious what all the three peaks represent in the Fourier transform. Are they all different depths? So is one, for example, the depth of the aerogel, and the others two are, say, the depths or the surface, the bottom of the aerogel, the surface of the aerogel, and then the sample? Is that what they are?
That's a great question. No, that's not exactly what they are. So these three peaks describe this equation up here. I can show you. So RR and RS are the reflection coefficients of the sample arm and the reference arm. That's your DC component that we call. So it's centered at 0. I should have probably put a number on the z-axis, on the x-axis here. The center at 0, that's just your noise, so you can get rid of that. This is where your depth information is in the cosine. And because it's cosine, when you do a Fourier transform, there's something called cosine ambiguity, so you don't know which side of the 0 is your depth. We always assume it's on the positive side. So essentially, you just don't look at these two peaks when you do your data analysis, and you fit for this peak in the center here. And this is for like a single surface. So just the top surface. And all the surfaces, the data would look like something similar to this, but the peaks would be shifted depending on where they are.
Perfect. Thank you for that. Are there any more questions? I don't see anything in the live stream right now. Any more in Zoom? Feel free to put your hand up. All right. Well, if not, I think we can leave it there. Thank you very much for the presentation, Avani. We all appreciate learning a little bit more about Helix and about your studies with aerogels. Yeah, so if you are in the live stream, or if you're interested in coming back to the talk, it has been recorded and will be up on YouTube. But yeah, thank you all for coming by, and thank you again, Avani, for giving us your presentation at this month's HQP seminar.
Thank
Hope everyone
you.
has a good rest of your day.